Okay, the specific question I'm going to look at today is how do we handle the edge of our metadata tag systems, where we have to deal with sort of raw, untagged data. We may have devices that are legacy devices that haven't been designed to speak tags directly, and we may have DMA, this sort of legacy DMA that would like to write into our memory system but doesn't know anything about tags. So that's what this talk is going to focus on. Just to remind everybody and get you up to speed on our security architecture, our DOVER is a security enhanced RISC where we've added this programmable unit for metadata processing, a pump, in order to support software-defined metadata processing. That means that we've added tags to everything. We've added this metadata tag so that we know some information about every word in memory that we're dealing with. This allows us to know things like type, is this an instruction or an address or a floating point value, where it came from, what are the extents of a buffer, and what's the secrecy on this data. Then all of this data, as it's processed, we mediate every operation. That's what our pump's doing. It's looking at this data that's coming in and supporting this software policy so we can enforce safety and security policies. So we can do things like make sure that we're supporting memory safety, making sure that we're supporting control flow integrity, that we're checking the integrity of the operations, perhaps supporting information flow. So that's what we're trying to achieve, and that's what we talked about last time about how we achieve that for the processor. So the challenge that we want to come back and address today is how do we deal with it in the case, if we really look at it, the processor's not the only thing that wants to talk to our memory system. In these things, we usually have other entities out on the bus. In particular, for performance, we often have DMA devices that would like to be reading and writing to our memory without having the processor intervene in that operation. So we know why that's useful to handle our buffers and to stream our data around, but that presents a challenge for us. If we don't do anything about this, this could potentially undermine our security. The DMA device might scribble over some piece of our OS and change its operation, or it may be able to go in and grab some piece of secret data that we hadn't intended to release from our system. So that's what we want to address. Now, on the slave side, this is relatively easy, so let me go ahead and talk about that and knock that off. The slave devices, the processor and the existing pump, is going to mediate things. Now, we would like fine-grained control over what happens there. And so what we do is we do allow ourselves to tag, to provide tags for these memory operations. And we can use that to write rules to control access to it. So we have our slave devices like typically a UART, maybe an I2C, maybe even the configuration on your DMA. We're going to perform an operation to that, but it's under processor control. But we'd still like to see a tag for those operations so that we can control sort of who can write to it, right? So if that provides a tag, we can control it at a fine-grained level, not just is this machine mode or is this kernel mode versus user mode, but maybe at the level that this piece of the code running with this authority is the one that's allowed to access this. This will allow us to do things like perhaps give configuration control to a particular device driver without opening up the possibility that device driver could muck around with other devices or do other special things in our system because we have this fine-grained control. It allows us to also do things like to mark our data coming in from the memory map devices as things that are untrusted and perhaps even mark them by source so that our software can properly handle the management of that data as it comes in, so we don't end up being confused in things like SQL injection attacks. So on to the kind of the richer DMA type things, we'd like support policies on our DMA IO like we're supporting policies on the processors. For example, we may want containment. Typically, we do have a clear idea of this is where this DMA device should get its output buffer. And so we say, okay, this is the region that you can read for your output buffer. This is the region you're allowed to write for your input buffer. We'd like to have this integrity so that even if our DMA engine is writing data directly in there, we'd still like to mark this as untrusted data that we don't use at least until it's been sanitized on the way in. From a secrecy standpoint, we'd like to make sure that it doesn't grab secret data that hasn't already been encrypted and is ready for exit, and we can enforce policies on that. And we can also use this to support synchronization so that we only grab data that's already there, not bogus data in an empty buffer, and similarly mark data as it comes in. So these are the kind of things we'd like to support. A reminder is that in our software-defined metadata policy, we have these kind of programmable, very rich functions that we can support based on the data that's involved in the operation, right? So that's which operation are we performing, and what are the metadata tags on everything that's involved. The PC, the current instruction, the inputs, the register inputs, and any memory inputs that come with that as well. So that's our input to our function. We get to write any function that comes out of that. The main thing we want to know is it's allowed. Is this a legal operation? And if it is a legal operation, then we'd like to know how do we update the PC tag and how do we update the result that may come out of it. So that's the basic policy that we've been supporting in our SDMP, and we're supporting on the processor. So we'd like to extend that to dealing with our I/O. Okay? So we're going to use the same function, same functional form. We want this as a unified policy. Now, for slave devices, this is relatively easy. Once we find a way to present the tag associated with the slave device, the pump that's running for the processor can check and say, this is what this is, and maybe say something about how the tag on the result should come out of that. For the DMA type operations, we're going to have to extend it. We're going to recognize that there's a set of operations there, DMA load and store. So we designated DMA load and store. Now, when it's coming from DMA, we've got a different PC, if you will, which is the state of that particular initiator, that particular DMA unit. That's when it's going to come in as our PC tag. Then, as we want to know which DMA unit, which initiator is it coming from, we'll set that up as the instruction tag so that we can write things and say, okay, maybe this network controller is allowed to write to this buffer, and this other one's allowed to write to this other buffer. And we can separate that if we'd like to. The data that's coming in is public untrusted, so that's going to be sort of implicit. And then the key thing in here, the memory tag, the memory that it's writing or reading from, we're going to get that as the MR tag. And if it is writing the result out, then that's what the result tag from this operation is going to perform. Now, let's talk a little bit about kind of what does misbehavior mean in the standpoint of a DMA device. When it was execution on the processor, our simplest answer is to say we shut down the offending process, right? And so kind of you can shut that down and other processes can continue to run, and you isolated yourself within the system. In this case, DMA is not necessarily associated with one particular process, and so it's going to, in some ways, it's its own process, and we need to think of it like that. So we have a couple of models we can think of. The one that's closest to the shut the process down is the one where we shut down a particular DMA device or initiator. And so that we can do simply by setting the PC tag on the output to disabled, and we've configured that we've distinguished this disabled so that if it's a disabled device, we'll just discard its results from there on out. So we kind of set the result to the PC tag, the state of the device, to disabled, and then we don't listen to its operations anymore. And it's disabled until some supervisor or something comes back and decides, oh, we've reset that device, let's reset its state. Now, that may be too extreme, so we also provide a model to say, well, maybe I'd just like to redact that particular operation, in which case we're going to set the tag on the result to say discard, and we'll discard that operation. If it's a write, we just won't allow that write to occur so nothing gets corrupted. If it's a read, we'll zero out the data so that we don't end up sending out any data we had not intended of sending out, but otherwise we'll allow the device to continue. So when we put that together, here's a picture of kind of what the DOVER SOC might look like. We have the top of the world up here, which is all tagged. So we have a tagged fabric, we have tagged data, the operations are from the processor, and everything's mediated by the pump. The bottom side here is the sort of untagged piece of the world, our interface with the outside world. So this is untagged, it's an untagged fabric. Mediating between those two, we have this I/O pump that's supporting these rules on the I/O operation and a device tag register file. If we're doing a slave operation, that's still going to be checked by the pump, but the device tag is going to provide the tag for the memory map device, if the memory mapped device can't provide it itself. And then the pump can enforce the rules. For a DMA operation, that's going to be initiated through this direction. The I/O pump is then going to go fetch the tags associated with it, process the rule, and allow the operation to complete only if the tag allows it. Internally, we can pipeline this I/O pump so that we can run at full throughput, so that we're limited by only the throughput of the memory system and not by the latency of the round trip operation. So we can go in, fetch the tags out of them, get them back. Once we package that up, feed it through the I/O pump to see if it's validated. If it's validated, then allow a write to occur or return the read result. Now, to integrate this in the RISC, the I/O pump ends up generating an interrupt when there's a rule miss. That allows us to demand page in or demand fault in the rules from the software into our I/O pump as we do with the regular pump. The I/O pump and the device register file, which you just saw, are memory map devices. So that's how the software can communicate with them and get them set up. Device tags themselves control access to the I/O pump and the device register file so that we can write rules appropriately and make sure that only the appropriate supervisor system, usually only done during boot, gets a chance to set these things up and in mishandling. The I/O pump CSRs are similar to the pump CSRs that we have. Mostly those are the inputs and outputs to the rules, so that the software-defined metadata processing software can go in and insert the rules appropriately when there's a miss. Our mishandler uses the same rule. It's a one unified function between the one that runs for the processor and the one that runs for the I/O pump. That's what we want, since we want some uniform policy enforcement. They get dispatched from an interrupt in this case rather than a trap because of where the I/O pump sits. And insertion in is through these memory mapped I/O pump access instead of RISC-V CSRs. So putting that together, what we see is if we really want to, if we want to protect our entire system, that means we have to manage the edge of this system, the edge of our world, where tags sort of cease to exist or where tags begin to exist as data comes into our system. We say that we can do kind of complete fine-grained mediation of these things for all of our actors, including our DMA IO, and we maintain this uniform software-defined metadata processing to the edge of our system, including the slave devices and mediating the DMA devices, even if the DMA devices themselves aren't aware of tags. So with that, I'm happy to take questions.
Thanks, Andre.
Thanks. This is Tron from NVIDIA. For the tag-based protection, what's the granularity for your data protection? For example, you trigger a DMA to access the data, then you will based on the operation source date and the destination buffer to check whether DMA operation can be operated. Then, did you set protection based on the data, or a specific address range for the data, or the whole DRAM for the DMA operation? Thanks.
Okay, so the question was, what is the granularity of protection on these operations, right? The granularity of protection is at the word level. So for an RV64, that would be at the 64-bit word. And that's what the tag, we've got a tag on each one of those things, and the tag on each one of those things ends up telling us what we're allowed to do with that. Now, it's a little bit better than that, in that in our actual implementation, we keep information we keep track of the byte enables. And so we expect in most cases you're going to operate things on words, but we have the ability for you to express information at the byte level in cases where you need to do that. That's going to put more pressure on the pump, but it's expressible within our system.
So the error impact will also be bigger?
The simplest model is that we're putting 64-bit tag on a 64-bit word, which means we're doubling the memory. We do lots of things behind the scenes in order to compress that, so you don't really see that full cost in the system.
Thanks, Andre.
Thank you.